Hello, I'm Russell Burton, the Program Manager for the FGR's program, the 21st Century Tissue Culture. I look forward to actually providing an overview of that with you today. Tissue Culture Partnership is an industry-government partnership aimed at speeding up the deployment of the best radiata pine genetics available. This was identified as a priority by the Forest Research Council. The basis of the program is to industrialise somatic embryogenesis of radiata pine and position it such that the opportunity to use varietals in commercial forestry is substantially expanded, providing real benefits in the supply chain and in the forest. Tissue Culture Partnership is now entering its third year. The purpose of this short presentation is to provide an update, reminder of what we're doing and why, who is involved, and the progress that is being made. Continuing focus on profitability from forestry, increasing environmental pressure, the risks from pests and pathogens, combined with the impact of climate change, along with the usual commercial demands on increasing wood quality and uniformity, puts pressure on tree breeding and realising the benefits from the products of that work in breeding. This is not a tree breeding program, it is a deployment program. Our focus is to create an opportunity for rapid deployment of targeted genotypes as varietals, helping and delivering the benefits and the qualities of trees in any given stand, but also delivering greater stand uniformity and growth uniformity over using families, which creates cost saving to the forestry company. The foundation of the program is somatic embryogenesis, a process that starts with cultivation of immature zygotic embryos formed after controlled pollination and extracted from green cones. The embryogenic tissue can be cryopreserved, and this cuts to the heart of the real advantages of somatic embryogenesis over other techniques of vegetative propagation, and that you can subsequently propagate from proven genotypes. When you know you have a top performer, you can just take that cell line out of the cryotank or liquid nitrogen and start propagating it from it, hence the ability to focus on known performers and elite genotypes. From there, we focus on the maturation and germination steps. Currently, there is an additional step of organogenesis used for multiplication and to support rooting. Although this is still an option for us, our ideal is to be able to take somatic embryogenesis material directly and go straight to the ex vitro step, putting these plugs into plugs and then into the nursery. And that removes the extra ex vitro step. Through exploiting other technologies, such as the use of bioreactors, robotics and automation, it lends itself to scalability and also the potential to be a very cost-effective process for propagation. This assumes we can develop large quantities of mature embryos and do this consistently. Somatic embryogenesis is not new. It's already used in New Zealand. The current practice uses transference and retransference of the embryogenic tissue and developing mature somatic embryos in semi-solid gel media, and this is quite a labour-intensive process. The point of difference that we seek to exploit is to use liquid media in bioreactors to proliferate embryogenic tissue, allowing the emerging embryos to mature and then subsequently germinate. The composition of the media and the environment can be automatically altered as we proceed. No manual input is required. The use of liquid media lends itself to scalability and supports the use of robotics and artificial intelligence. Artificial intelligence to identify the good and the bad embryos, and robotics to undertake the transference process into the germination stage and later putting the plantlets into plugs ready for the nursery. In effect, this means that we have the potential to go from setting cell lines in the reactor all the way through to putting a plantlet into a plug without having to touch the biological material at any point, improving efficiency and using labour, ensuring sterility at all stages, and ensuring very exact control over the environment in which the biological material develops. It all sounds very simple, but of course it's not. We're having to develop new processes and learn how radiata will behave in these environments. It's not just about the science. We also need to understand how developing what will be a disruptive technology can fit into existing supply chains. And to that end, although Scion leads the science, we have several very experienced science collaborators. For example, Georgia Institute of Technology in the USA, who have a lot of experience in using temporary immersion bioreactors and also experience with robotics and automation and application to trees. They've also developed a prototype of a robotics artificial intelligence system called the Fluidic system that can transfer mature somatic embryos from a bioreactor, undertaking the germination stage, and then later from this to positioning the plantlet into a solid plug ready for transfer into a nursery. We've been able to work with their system to improve and modify its use for application to radiata pine. We're also working with the Natural Resources Institute of Finland, LUCA, who have a vast amount of experience with somatic embryogenesis, although not with radiata pine, but exploiting their knowledge and taking SE-derived plantlets directly into a nursery environment, and also their experience with cold storage of this type of material. Critically, we have a lot of support from industry, including Timberlands, Arborgen, the Radiata Pine Breeding Company, Proseed, Olson's, Matariki Rainier, and Hancock Forest Management. Challenges we have to address are many. For example, the use of temporary immersion bioreactors with radiata pine is pioneering new territory and technology. And we all know that much as we love radiata pine, it is not an easy species to work with at a cellular level. We also know that genotypes behave in different ways. The application of robotics and artificial intelligence to radiata pine, again, pioneering new territory, but leveraging off the experiences at Georgia Institute of Technology and with other species. The ability to successfully transfer somatic embryogenesis material into nursery, that too is another challenge. And the impact of how this will all fit into supply chain, and of course the attitude of those planting forests to more extensive use of varietals. And of course the inevitable question of how much would a plantlet develop through this approach cost. The challenges are substantial, but the rewards are very substantial. And I'm pleased to report that across the board, we're getting results that give us confidence. We don't have all the answers yet, nor are we pretending that our vision's been delivered on, but that the results are giving us confidence as we proceed. For example, Scion now has a suite of temporary immersion bioreactors. They have some 96 of these, all able to be programmed and remotely controlled. These operate by temporarily immersing the developing tissue material in liquid, which contains the various hormones and nutrients required at the different stages in development, being able to adjust the composition and time as they proceed. And it's all done remotely and managed by a computer. We have successfully used these to proliferate and mature some somatic embryos from Scion's cell lines. The big task now in front of us is to extend that to other genotypes. To give us increased control over the environment in which the tissue develops, the program has developed a more advanced bioreactor that enables much greater control over the internal environment within it, such as the humidity and the internal gas composition. Our intention is that we'll be testing these systems fully out over this coming year. The above experimental program is being closely duplicated at Georgia Tech. This is useful as it provides not only experimental robustness, but also helps learn from their experience, transferring their knowledge to New Zealand. We also need to be able to take the plantlets arising from somatic embryogenesis process directly into the real world. To that end, Scion and LUCA have been looking at taking SE-derived plantlets and looking at the different time on germination media, the impact of cool storage, and different lighting regimes to enhance germination of mature somatic embryos and improving the quality of the rooting system using different microplugs and time. Taking the plantlets derived from somatic embryogenesis into the real world, we know that typically the resilience of pure SE plants has been poor, as has the development of robust rooting systems and an ex vitro multiplication step has often been required. This is still very much work in progress, but we are progressing with confidence. We know that there are enormous gains to be made if we can avoid the extra ex vitro multiplication step, and so any success here will provide very significant gains and another step towards achieving our vision. Understanding the context in which the processes we are focusing on can be used commercially is also an important part of the program. In that respect, the Industry Advisory Group has been especially valuable. We have also undertaken some other consultation with industry with a specific focus on nursery growers. So far, we're not hearing any concerns over the use of varietals. In fact, it's been uniformly positive, although the question always comes up, and how much will it cost? The form and the size of the ultimate product is also of special interest, including the particular focus on rooting. It's too early to be able to give precise answers to these questions, but understanding the market and the supply chain is very helpful in helping us shape the focus of the actual science itself. Although I stress this is a propagation program and not a breeding program, the reality is that there is a very strong interrelationship between the two. We already know that some genotypes will create greater yields and more robust germinants through use of somatic embryogenesis than others. Perhaps we will get to a point where performance for somatic embryogenesis becomes a key criteria for breeding itself. This, combined with the ability to store cell lines of known performers and cryopreservation, would lead us to a very strategic approach to forest development and an important building block in the move towards precision forestry. We're now into our third year. I feel that we have a solid platform and strong partnerships to build on. The big challenge in front of us now is to build the best knowledge platform we can as the basis of what could be a very significant development for the New Zealand forest growing industry. Last but most importantly, I want to acknowledge what is a very substantial and very significant science team across three nations. I also want to acknowledge the technical advisory team whose advice has been gold, and the governance team whose time and commitment is very much appreciated. So on behalf of the science lead, Associate Professor Jana Klasnikova, and the wider team, very much thank you for your time and your interest.